Hello guys, my name is Devam Shah. I hope everything is going well during this pandemic course of time. So without any further ado, me and my teammate would like to present our paper presentation on virtualized congestion control. I will give the first basic overview of the virtualized congestion control of what the authors are trying to accomplish here. So let's start. Virtualized congestion control are implemented to reduce latency increase throughput and fairness in between virtual machines. This makes the client happy because they are getting speed that they wanted, and the data center happy because this makes their business more efficient and profitable. Usually, traffic goes from various virtual machines to the data center. The authors have created a software that is controlled by data center called hypervisor. The hypervisor is a place on the network in between the data center and the virtual machine. All traffic will pass through the hypervisor, and within the hypervisor is the virtual congestion control layer. This is where the congestion control layer algorithm goes. Not all virtual machines have the new congestion control algorithm. In order for the old virtual machine to benefit from the new congestion control algorithm, we need the hypervisor. The hypervisor is the hypervisor is the important because it transfers the congestion control algorithm between the new and the virtual machine that don't have any algorithm, or even if they have their own algorithm. This means that it will it will seems as if all virtual machines that are connected to the data center will have the new algorithm. Sounds too complicated, right? But these layer systems and even recent systems have their own congestion control to make themselves more efficient. When they send their data out, they think that their own algorithm is working. However, the hypervisor is located in between the data center and the virtual machine. When the data comes from the virtual machine to the data center, then it passes through the hypervisor, which translates the overlay algorithm, which can be guessed as virtual congestion control algorithm. Now, this algorithm is translated and it overwrites the data to the data center network. Now, underlay algorithm is a part of this algorithm, which means that guest won't know the data is being translated and it has been using another algorithm other than its own. So, yeah, here we can see that the give me 1 second. I have just gone through all this introduction layer. Yeah. Here we can see the traditional data center setup that there are tenants containing virtual machine, which means in the tenants are infrastructure of the data center, which holds those virtual machine. Each virtual machine is a different client, and while using the virtual machine, it may seems like it's a standalone machine, but multiple clients share the same infrastructure, and this infrastructure connect to the data center. The green, yellow, and orange red represent the traffic that passes to the data center. So, as I said that I have covered this introduction topic for the all virtual condition control algorithm for overlay and inlay, and the last part was the traditional data center setup. So let's get to the second picture for the more clarity. As a picture words thousand words, because as I said that I have gone through the introduction to be more clarified, to give a more clarity. I'll give the introduction that how the packet moves. So here the data center is responsible for the moving data efficiently through the network. As you can see, the infrastructure have a queue, and once this queue fills up, the performance is unstable. Some of the packet get lost, and another take a long time to get the destination. This is when congestion occurs. This is an issue. This is an issue becomes some clients will not get the level of service that they expect. With one problem of data center, is congestion occurs in this infrastructure. Congestion can also occur in just one virtual machine in the same way if the queue fills up for the one virtual machine congestion, and the secondly it will occur on the causing the same problems. Data centers are not able to utilize the resources efficiently because of these issues. However, by using congestion control algorithm, it can reduce congestion whether of an inch on either on the infrastructure or on a single virtual machine, allowing the packets to be sent through a shared line from other virtual machine in the same infrastructure, making the backed up virtual machine even faster than before. So, congestion control algorithm are around for a while now. Hmm. Yes, the data center and the virtual machine communicate directly using these algorithms. For example, CDC had the same similar work where the modified TCP header for every virtual machine in the infrastructure. The problem with this is that every virtual machine has to be modified for the algorithm to work the framework that is introduced in the paper. Addition to this, the software in the between the data center and the virtual machine called the hypervisor. This one. Using the hypervisor, it is possible to communicate with the whole legacy systems and the new system without adding the TCP header for any other virtual machine. The virtual machine hypervisor automatically translates the algorithm. There is an also ease in implementing the congestion control algorithm in the hypervisor. Rather than rather than implementing in each individual virtual machine or having to worry about legacy system from the test runs, we can see later how efficient it is and how well it will work with the old legacy systems. Here we can see there are congestion control algorithms added in between some of the virtual machine in the data center, while others don't have any congestion control algorithm added in some between of virtual machine and the data center. Yeah, this will become more clarified that how congestion occurs and how the system got unstable due to the hypervisor and how the hypervisor will perform some kind of action to prevent the congestion. While others doesn't have any congestion control algorithms, the ECN had. So let's just go to what is ECN. As I said that the TCP header for any other virtual machine, the virtual machine automatically transfers the algorithm, and it has a ease to implement the condition rather than in applying in individual virtual machine. Yeah. So while others don't have any condition control algorithms, the ECN is an explicit congestion notification which was introduced in the paper. It can modify TCP header to give notification of congestion to sender. It also prevents packet from dropping unless the sender sends an additional message to the receiver that the packet is on the way. We will soon see the picture of how ECB enables the flag to indicate support ECB is critical to virtualize congestion control. The ECN, yeah, this one. This is the all the theory of the ECN that I have been explaining for the TCP header and the acknowledgement thing. So let's just go. What is the ECN and how the ECN flows with five to non ECNs, from nine non ECNs to one ECN, from one non ECN to nine ECN. So what this picture indicate and what does it signify? So by using them together, the VCC will able to tell where the congestion is occurring. A queue management system such as random early detection will also be used with the ECM. The issue, if the legacy system doesn't have an ECN, it will be solved because the hypervisor will have ECN built into it. This is how legacy system won't know if the data is being transmitted because it's all done in the hypervisor after it is left virtual machine. The author did a congestion control testing using ECN, and together three tests were done with the 10 flows of 10 flows in a shared 100 megabyte per second bottleneck. In the first test, uh, the shows which shows the good put of 9 and 1 ECN. Here we can see that ECN works perfectly fine with the 9 ECN, and in the second test, we compared the 5 with a 5 ECN with the 5 non-ECN. Here we can see there's a significant difference. The ECN flows are slightly better good put than the 5 non-ECN flows, and even better good put from the previous test. And the 5 non-ECN flows have decreased the good put from the previous test. This is where we can see the impact of the good put between the ratio of ECN and the non-ECN flows in one bottleneck link. In the third test, we compare 9 ECN flows and 1 non-ECN flows. Now we can see a huge difference where one non-ECN is starving and has almost no good put, but the 9 ECN flows are using all of the bandwidth. This shows that the ratio between the ECN flows and the non-ECN flows increased towards more ECN flows. The goodfoot of non-ECN suffers now. We don't know now we that know that how ECN affects goodfoot without a hypervisor. Let's back let's get back on to the author while implementing the hypervisor and how this ECN will never systems in the same bottleneck link as non-ECN with the older system. Here's the idea. It's how we have a data center on the right and the guest virtual machine on the left side, and in the middle part we have implemented a hypervisor, which is located in the VCC transition layer. We can see that the VCC transition layer inside of the legacy system. Systems only communicate between the hypervisor and the guest virtual machine, which enables transition between non-ECN machines and data center. The data center controls the congestion control algorithm, which is sent to the VCC transition layer. The VCC can then modify the previous congestion control algorithm and change it to a new one. These are the introduction to the fairness mixed ECN environments, or we can say that the techniques which are involved for the hypervisor. So this is the completely overview of the hypervisor techniques. So I'll be discussing a little bit of that. Different techniques are introduced, but the main focus on two techniques were the throttling the receive window, which makes the connection window useless because it relies on the receive window, and the modifying the three-way handshake, which requires additional techniques. There is one general method data centers can use in manually modifying the switches and rules to tweak the fairness. But this means that if they ever add more tenants, they will have to manually make modifications again. So now let's talk about the hypervisor transition technique. Now from these techniques, my teammate John will take over.
The purpose of this research was to use a better congestion control algorithm in the multi-tenant data centers while not being concerned with TCP friendliness with non-participating virtual machines. The authors of this article emphasized throttling the receive window and modifying the three-way handshake.
Throttling the receive window relies on the receive window and modifying the three-way handshake. This means the congestion window will not be used. One general method a data center can use is manually modifying the switches and rules to tweak the fairness, but this means that if they ever add more tenants, they will have to manually make modifications again. The hypervisor has many TCP modification techniques that our virtualized congestion control architecture can use. I will now go over them, starting from most intrusive to least intrusive. Our most intrusive technique is called write into guest memory. In this technique, the hypervisor directly modifies the congestion control algorithm. This is achieved by writing the TCP parameters in the corresponding guest memory and registers. Unfortunately, with this technique, processing and communication delays occur when the hypervisor accesses the guest memory instead of keeping an internal state machine. The second technique is called read from guest memory. This technique does not write over the memory and instead monitors the memory using the guest introspection. Unfortunately, instead of keeping an internal state machine, the hypervisor accesses the guest memory. This adds communication and processing delays. The third technique is called split connection. In this technique, a TCP proxy is used to break a 232 TCP connection into several subconnections. At a chosen rate, it can acknowledge the packets into the guest virtual machine. Then, the packets are sent on the data center network using target congestion control algorithm. Unfortunately, a barrier-based application may believe that all its packets were ACKed and continue when the packets were not received. Buffer packets is our fourth technique. This allows in-flight packets to be buffered by the hypervisor transition layer. The packets can then be resent without informing other guests. Unfortunately, large buffers significantly increase the memory footprint of virtualized congestion control. Buffer ACKs is our fifth technique. The hypervisor can similarly buffer received ACKs. When an ACK piggybacks on the data, the sequence number is reduced, and the remaining bytes are sent as a pure ACK. Unfortunately, the latency may also increase when the ACKs are delayed. With duplicate ACKs, the hypervisor can copy and resend the last sent ACK in order to half the congestion window of the guest. Unfortunately, this technique may violate TCP semantics. Our seventh technique is to throttle the receive window. The receive window follows the designated congestion window to make 4. Even though it does not appear to go against RFC 5681, the guest adapts to this target. Unfortunately, the receive window should not be decreased to less than the current number of in-flight packets. This creates conflict with common implementations of the TCP buffer management. By throttling traffic using the TCP receive window, we can give priority to certain applications without queuing or dropping packets in the network. The throttle window will make the guest adapt to the new environment by gradually decreasing the window while monitoring the connection state. However, since the receive window throttles traffic, we do not need the congestion window anymore. This can be a viable solution for most congestion problems, but it cannot be used if you want to make the TCP connection more aggressive. The second best solution is the three-way TCP handshake. When setting up a connection, the hypervisor can change the options that are negotiated. This is called the modified three-way handshake. The three-way handshake is between the state machine, the network, and the guest. The connection is made over a TCP connection. The hypervisor can change the maximum segment size of the packet if there is uncertainty that the maximum segment size of the packet can be handled at one time by a device in a single piece. Unfortunately, when modifying a three-way handshake and/or changing the maximum segment size, additional overhead for the data center and additional techniques must be applied. Now, we will solve for explicit congestion notification unfairness. We seek to improve the performance and fairness of the network by implementing virtualized congestion control in two distinct environments. The first implementation will be seen at the edge of the Linux kernel TCP implementation. This shows the virtualized congestion control aids in addressing unfairness between the explicit congestion notification and the non-explicit congestion notification in this Linux environment. The second environment is a proof of concept system in the virtual machineware, our ESXi hypervisors vSwitch. The first implementation uses the virtual machine running Ubuntu 14.04 with the Linux kernel version 3.19 or 3.13 for experiments, with 1 Gbps link executed with Mininet. The goal is to show virtualized congestion control can help address unfairness between explicit congestion notification and non-explicit congestion notification traffic in the Linux environment. Explicit congestion notification permits flows to respond to congestion prior to data loss. In the first experiment, an analysis was conducted between explicit congestion notification and non-explicit congestion notification flows. 10 senders were connected through a switch to a single receiver designed to be a native Linux guest without virtualized congestion control. The receiver can be viewed as a non-explicit congestion notification for non-explicit congestion notification flows, and vice versa. The second environment was a proof of concept system in the VMware ESXi hypervisor's vSwitch running Dell PowerEdge T610 server with a 12 GB of RAM and 2 Intel Xeon processors, about 2.4 GHz. The connection flows are divided into preferred and unpreferred flows. The transition layer is configured to divide the available window space among the unpreferred flows in absence of the preferred flows. The transition layer dynamically changes window space to preferred flows when it detects active preferred flows and divides the remainder among unpreferred flows. The virtualized congestion control provides a data center-wide coordination bandwidth allocation by controlling the end-to-end number of transmitting packets. Now, we will evaluate the hypervisor's bandwidth sharing. The DV filter is the virtualized congestion control's transition layer that is used as a filter in the hypervisor's vSwitch. Every per-flow state necessary for translation is stored in the hypervisor's own memory. Flows passing the switch are monitored by the transition layer. The transition layer also inspects the headers to maintain the correct state of information. When the virtualized congestion control transition layer decides to modify the headers, it changes the packet headers, recomputes the checksum, and then lets the packet pass through the filter. We will now demonstrate how we implemented the receive window throttling in this virtualized congestion control layer. The architectural complexity can be seen in the hypervisor switches that support an independent module with the ability to inspect, modify, and re-inject the packet. The hypervisor delay can be described as processing delays in the hypervisor that increase the latency. This increases the flow completion time and affects the RTT estimation found in the guest TCP algorithm. More benefit can be seen when the high-performance virtualized workloads bypass the hypervisor and directly accesses the network interference card with technologies like single root I/O virtualization. TCP segmentation, offload, and large receive offload are techniques used to increase the throughput of the high bandwidth network connections by reducing the CPU overhead. Delay-based congestion control suggests virtualized congestion control can translate to or from delayed-based TCP algorithms like Timely and TCP Vegas. The User Data Protocol, or UDP, is a communications protocol that is primarily used for establishing low latency and loss tolerance connections between applications on the Internet. This academic article emphasizes TCP. It is safe to assume the hypervisor would let the user data protocol traffic go through the transition layer in a transparent manner. With universal language, if we want to directly translate between n congestion control algorithms, we would theoretically need to implement the order of n squared translations. However, we can also use a universal atomic congestion control protocol, allowing us to use 2n translations to or from this protocol. And with encryption, this study indicates the virtualized congestion control architecture can be used for encryption services such as TCP crypt and IPsec, to legacy unencrypted TCP flows. And now debugging. Debugging adds packet processing modules to the connection endpoint. This makes debugging more complex when there are connection issues on a host. With inside connections, when two guests virtual machines on the same hypervisor communicate, they go through the hypervisor. This means they will also be passing through the same transition layer. Therefore, the virtualized congestion control will work without changes. With configuration, the network administrators can assign a different congestion control to different ports, IP addresses, applications, operating systems, or tenants in the virtualized congestion control architecture. With ADDC, this implies the data center administrators can seize control of the TCP congestion control for all virtual machines. The congestion control algorithm has the potential to adapt to the data network conditions. Our virtualized congestion control is used to adapt to the congestion control algorithm in the underlay network. The TCP rate of control is the sending rate of each TCP flow that is regulated by the ACT pacing and TCP rate control. Link level retransmissions in wireless communications, the SNOOP protocol buffers data packets in the base station and then SNOOP on ACKs. The lost packets are then retransmitted on the sender's behalf. This ensures the blocking of duplicate ACKs from reaching the sender. With split connection, using a TCP proxy, the split connection approach separates the TCP connection into several subconnections. With fairness between virtual machines, this method uses data center-wide isolation-based techniques which can enforce bandwidth guarantees while trying to maintain work, conserving link usage. The evaluation between explicit congestion notification and non-explicit congestion notification flows shows us that while the explicit congestion notification flows share the bottleneck equally among themselves, the non-explicit congestion notification flows become starved, as can be seen in Figure 4b and 4c. They cannot send as much throughput as the explicit congestion notification becomes more widespread. The ratio of explicit congestion notification and non-explicit congestion notification flows increases, and it can send fewer and fewer packets. Legacy applications have difficulty obtaining their packets via congestion, as applications increasingly adopt explicit congestion notification. Bringing in a similar amount of explicit congestion notification flows breaks the fairness between explicit congestion notification and non-explicit congestion notification flows. Figure 6 shows how non-explicit congestion notification flows impacts the other packets. Unfairness becomes larger when there are fewer remaining non-explicit congestion notification and legacy flows. Figure 11 compares non-explicit congestion notification and virtual explicit congestion notification flows. 11a shows 9 explicit congestion notification flows and 1 non-explicit congestion notification flow. You can see how the non-explicit congestion notification flows suffer from unfairness by how it is on the bottom of the chart while all 9 explicit congestion notification flows remain on the top of the chart. This means the explicit congestion notification flows have better output overall. In 11b, the non-explicit congestion notification flow is now virtual congestion notification, and it is now has a similar goodput to explicit congestion notification's goodput. The hypervisor defects the signature of a tenant port or packets and restricts the bandwidth used by the set of traffic. The bandwidth limit can be changed dynamically depending on signals from the network or the guest. After the introduction of preferred flows, the throughput of unpreferred flows drops as a result of the receive window throttling. This provides preferred flows with a larger share of bandwidth. The total throughput before and after the introduction of preferred flows remains relatively constant. Figure 9 depicts the send window time for a virtual explicit congestion notification flow for the virtual condition control experiment. This pattern would normally appear in the condition window. However, in our Linux implementation, when the receive window was the limiting window, the congestion window stayed larger than the received window for the entire experiment, which made the received window not needed. Figure 12 shows the results of an experiment done where the virtual condition control allocated the sharing of bandwidth. All hosts have different CCAs. These are the throughputs for 3 unpreferred and 2 preferred flows. These flows are receiving windows throttled by the ESXi virtual congestion control layer. The sum of the windows of all the live flows is kept constant. However, the virtualized congestion control throttles and preferred flows once preferred flow starting in order to give the preferred flow greater bandwidth. So in conclusion, the paper was well organized and well presented. The authors explained the different techniques used for congestion control algorithms prior to explaining their solutions to this problem. There were many graphs that explain the author's claims and how their solution can be improved in the future. We not only learned about congestion control issues, but we also learned various methods that have been used to quell and/or solve these problems. We learned the drawbacks of each method and how we can improve on each technique. Thank you for listening.